Mobile phones are ubiquitous handheld devices which can be used as touch-capable controllers in virtual reality. A key challenge is how to render accurate feedback of users' hands and fingers as they operate the phone in VR. Some headset sensors can track the hands and represent them as 3D models in VR, but current commercial systems have trouble consistently and precisely detecting the pose of hands holding objects due to occlusions, low angles, and limited range. We propose a system that can robustly and precisely track thumb and index fingertips moving above the touchscreen using the front camera of the phone. The images captured by the camera are reflected by two mirrors mounted above the screen at two different angles, which creates images from two different perspectives. Those images are fed to a deep neural network that estimates the 3D position of the fingertips. Combined with phone tracking, the inferred fingertip position data can be used to control hand models operating a virtual phone in VR. Our deep learning pipeline consists of three processes or phases. A data creation process to generate labeled ground truth data using a mostly self-supervised method, the training of a direct end-to-end neural network, and real-time inference of fingertip positions using the trained model. The images are first pre-processed on the phone. Frames corresponding to the two mirror views are cropped based on manually defined regions of interest and transformed into square images, which are used as input for the deep learning processes. The data creation pipeline consists of 4 steps and does not require any external sensor. After manually labeling a few images for initial segmentation, the process is also entirely self-supervised. The first step is collecting images from several people moving their thumb and index finger above the screen using the phone with the mirror mount. The second step extracts mask regions for the distal phalanges using the BassNet salient object detection network. The third step estimates the 2D location of fingertips based on the intersection of a polynomial fitting curve and mask contour. With the fingertip position, extra pixels not belonging to the distal phalanx region can be eliminated from the mask. Finally, the fourth step uses differentiable rendering to iteratively align the rendered silhouettes of a 3D phalanx mesh with the masks and 2D fingertips. This optimization process yields the 3D position of the fingertip in local space. That information is used as ground truth data to train a neural network that directly infers the fingertip position in real time from the input images. With mix-up data augmentation, simultaneous input with 2 hands, such as touch typing with 2 thumbs, can also be supported. The detected 3D fingertip can not only be used to control the fingers of virtual hands in order to provide visual feedback for precise touch input, but can also be used for a variety of 3D interactions. For instance, interaction with small 3D objects on and above the phone screen. Or single-hand double raycasting, combining a raycast from the phone and a second ray passing through the thumb tip to form a resizable lens, revealing a different layer of a map. The phone can also be fixed to the viewport to operate as a head-up interface, for instance, to select texture colors from a palette on the phone to assign to objects the user is looking at. Tracked fingertips can also control entirely different objects, such as a pen to sketch or erase content on the virtual phone screen, depending on which finger is used. In VR games, the fingertip can be mapped to a control point of a character, like the leg of a skateboarder, where dragging on the screen pushes the board forward, and above-screen finger gestures cause the character to perform mid-air leg movements. In a rowing game, the fingertip can control the oar of a character sitting in a canoe. Dragging the finger on the phone screen rows the canoe, and lifting the finger raises the oar to hit overhead targets. In a controlled experiment based on tapping and tracing tasks, we evaluate performance for single-finger touch input and compare 4 3D hand representations. A normal hand, a hand with markers on the fingertips, a simplified hand with stick-like fingers, and a 3D cursor, with 2 baselines, a flat 2D overlay directly showing the camera feed used in previous work, and a no VR condition where the phone is used normally. Results show that while VR performance does not yet match real-world conditions, the precision representations consisting of the hand with markers, the stick hand, and the cursor outperform the 2 other non-optimized VR representations for tapping small targets. For further details, Please see the paper.